For nearly 5 decades, Voyager 1 has traveled far beyond its original mission, which was to study Jupiter and Saturn. With no air resistance in space, once it gained speed, there was nothing to stop it. It's now moving at 61,000 kilometers per hour and will never come back to Earth. It is on a one-way path out of our solar system and is moving too fast for the sun's gravity to pull it back. Today, its signal is so faint that calling it a whisper doesn't do it justice. And yet that signal is still reaching Earth, showing just how incredible the engineering is that keeps this spacecraft alive, sending back data from a distance no technology has ever pushed to before. The faint signal that Voyager 1 transmits back to Earth is barely perceptible, less than 1/trillionth of a watt. To put that in perspective, this is the equivalent of a tiny radio signal lost amidst the background noise of space. The signal is so weak that it would be undetectable to most modern receivers. Yet, against all odds, NASA listens for that faint echo, using its vast array of specialized antennas scattered across the globe. These antennas, some as large as 70 meters across, amplify Voyager 1's whisper, allowing scientists to reconstruct data from it at the astonishingly slow rate of just 160 bits per second, far slower than the dial-up internet speeds of the 1990s. The spacecraft's signals take more than 23 hours to travel to Earth, a testament to the vast distances separating us from this distant Voyager. To download a single photograph from the spacecraft at that rate would take weeks, underscoring the immense technological challenge of communicating across such a great expanse. At launch, Voyager 1 was powered by 8.8 kilograms of plutonium-288-298, a material that decays slowly and generates heat. This heat is converted into electricity by a radioisotope thermoelectric generator, RTG, providing enough power for the spacecraft to run its instruments. At the time of its launch, the RTGs generated 470 watts of power. But like all energy sources, this power has waned over time. Today, Voyager 1's RTGs generate only around 200 watts, losing roughly 4 watts per year. As the power decreases, NASA has had to shut down instruments one by one in order to extend the spacecraft's life. Some instruments, such as the cosmic ray sensor, were turned off as recently as 2026 in an effort to conserve power and ensure that the remaining vital systems continue to function. Despite the limitations imposed by its diminishing power, Voyager 1 continues to operate, and it is still capable of returning scientific data. However, its ability to send and receive commands from Earth is not as simple as it may seem. There is exactly one antenna on Earth that can communicate with Voyager 1, Deep Space Station 43, located in Canberra, Australia. This antenna is the sole link between Earth and the spacecraft, and it is crucial for any communication or commands sent to Voyager. But this connection is not always reliable. DSS-43 will be taken offline for a major upgrade, meaning there will be no way to send critical commands to Voyager 1 during that time. If the spacecraft were to experience a critical fault during this period, NASA would be forced to wait months before they could act. This represents a stark reminder of how fragile the connection is between Earth and Voyager, and how vulnerable the spacecraft is as it continues its lonely journey through space. Voyager 1's aging systems are another challenge. The spacecraft was built using technology from the 1970s, an era when computing power was a fraction of what we have today. The onboard computers are primitive by modern standards with limited memory and processing power. Yet, despite these constraints, Voyager 1 has continued to function, its systems operating for far longer than anyone ever anticipated. NASA engineers have had to develop clever workarounds to keep the spacecraft operational. They have relied on redundant systems, swapped out faulty parts, and used software updates to prolong its life. It is a testament to the ingenuity of the engineers who built and continue to maintain the spacecraft, using every ounce of power available to keep it alive and transmitting. Yet, as impressive as the spacecraft's longevity is, it wasn't designed to last this long. The Voyager mission was originally expected to last only 4 years, long enough to reach Saturn and complete its flybys of Jupiter and Saturn's moons. Anything beyond that was considered a bonus, a chance to gather additional data as the spacecraft moved farther out into space. But Voyager 1's trajectory took it beyond the boundaries of the solar system, into interstellar space. It has continued to send back data on the environment beyond the solar system, providing invaluable insights into the conditions of the outer reaches of the sun's influence and the interstellar medium beyond. These data are not just a bonus, they represent a unique window into the nature of space beyond our immediate solar neighborhood, a place we have never before been able to explore. In 2012, Voyager 1 officially crossed the heliopause, the boundary where the solar wind ceases to dominate the environment around the spacecraft. This was a pivotal milestone in space exploration, as it marked the first time that any human-made object had entered interstellar space, the space between the stars, far beyond the influence of the Sun. The crossing of the heliopause meant that Voyager 1 had left the protective bubble of the solar system, entering a region of space never before explored. It was a significant achievement, demonstrating the spacecraft's durability and the successful execution of a mission originally designed for a far shorter lifespan. This crossing was not only a technical triumph, but also a symbolic milestone, representing humanity's first step beyond the edge of our solar system. Since its departure from the heliosphere, Voyager 1 has continued its journey outward, gathering data that expands our knowledge of the broader universe. As it moves farther from the Sun, it is providing key insights into the interstellar medium, including information on the density and composition of the space between stars. The spacecraft's data is helping scientists study the nature of cosmic rays, magnetic fields, and plasma waves in a way that was never before possible. Although the signal from Voyager 1 is becoming weaker with distance, the valuable data it is sending back is expected to shape scientific research for years to come. The spacecraft will continue its solitary voyage for billions of years, far beyond the reach of human civilization, leaving behind a legacy of exploration and discovery in the deepest parts of space. Voyager 1 is not alone in its mission. Its sibling, Voyager 2, was launched just 16 days after Voyager 1 in 1977 and has followed a similar path, also exploring the outer planets and now traveling into interstellar space. Both spacecraft were originally designed to conduct flybys of the outer planets, with a primary focus on Jupiter and Saturn. After completing their planetary missions, both spacecraft were sent on trajectories that would take them beyond the influence of the Sun, into the vastness of interstellar space. One key feature both spacecraft share is the golden record. This 12-inch, gold-plated copper disc contains sounds and images that represent the diversity of life and culture on Earth. The golden record was created as a message to any potential extraterrestrial life that may encounter the spacecraft in the distant future. The disc contains 16 photographs, including images of human anatomy, landmarks, and scientific concepts. It also includes sounds of nature, like thunder, birdsong, and the sound of a kiss, as well as greetings in 55 languages and music from diverse cultures. These include pieces from Bach, Beethoven, and a traditional Peruvian pan flute. The record also features a record player and a needle to play the messages. The purpose of the golden record was to serve as a time capsule or representation of humanity that would outlive the spacecraft and potentially reach extraterrestrial civilizations should they ever intercept the signal. The message encoded on the disc includes instructions on how to decode it, though it is unclear if any future civilization would have the means to read it. As of now, the Voyager spacecraft are the farthest human-made objects from Earth, with Voyager 1 being over 15 billion miles away and Voyager 2 about 12 billion miles. Both are now traveling in interstellar space, far beyond the heliosphere, the bubble of charged particles and magnetic fields created by the Sun. Voyager 2 crossed the heliopause in 2018, making it the second human-made object to enter interstellar space, after Voyager 1, which crossed it in 2012. While both spacecraft are still transmitting data, the signals they send are incredibly weak. At their current distances, Voyager 1's signal has decreased to less than 1 trillionth of a watt, and it takes over 22 hours for the signal to travel from the spacecraft to Earth. The spacecraft are powered by radioisotope thermoelectric generators, RTGs, which convert the heat from the natural decay of plutonium-238 into electricity. Over time, the power from these RTGs diminishes, and the spacecraft have been carefully managed to conserve power, shutting down non-essential instruments to keep the critical systems alive. Despite being far beyond the reach of direct communication, both spacecraft will continue their journey for billions of years. Voyager 1 in particular is moving at a speed of 61,000 kilometers per hour and will eventually pass through the Oort cloud, a distant region of icy bodies surrounding the solar system. However, neither spacecraft will ever return to Earth. They are on a one-way path, traveling too fast for the Sun's gravity to pull them back. The spacecraft will continue drifting through space, potentially for billions of years, as silent messengers carrying the story of humanity into the cosmos. Even though Voyager 1 is the farthest human-made object from Earth, it is not without its vulnerabilities. The spacecraft's power will continue to diminish over time, and eventually, it will no longer be able to communicate with Earth. Its instruments will cease to function, and the spacecraft will drift silently through interstellar space, a testament to humanity's ambition to explore the cosmos. The engineers who built Voyager 1 never could have imagined that it would still be functioning more than 40 years after launch. Yet, thanks to their ingenuity and the power of nuclear energy, the spacecraft continues to send back data from the farthest reaches of space. This persistence, however, is not without a cost. The engineers who maintain Voyager 1 are forced to make tough decisions about which instruments to turn off and which to keep running. Every watt of power is precious, and every decision can extend or shorten the spacecraft's life. The science team continues to monitor the spacecraft's health, carefully analyzing the data it returns and ensuring that it remains operational for as long as possible. As time goes on, the decisions become harder, but one thing is clear. Voyager 1 has already far exceeded its original expectations, and every new piece of data it returns is a bonus, a gift from the farthest reaches of space. Voyager 1 is a true example of human creativity and determination. It's a spacecraft that has beaten all expectations and keeps pushing the limits of exploration. More than 40 years after it launched, its journey is still going. As it travels farther into the unknown, it reminds us of our ability to reach beyond what we know, explore what's out there, and leave a mark on the universe that will outlast us. Voyager 1 isn't just a spacecraft. It represents our drive to discover, proving that no matter how small or fragile we are, we can still reach for the stars.